Hello and welcome to the Unit 3 podcast on section 9.5, which is Electronegativity and Polarity.
So I am Mr. Lin.
I'm Mr. Sakaguchi, and let us start. Oops.
There you go.
Okay, so when we're talking about intermolecular forces that hold covalent bonds together, that attract them, covalent compounds together, we're looking at electronegativity differences. So not every covalent bond is created equal.
Well, you already had a little bit of an intro of this stuff when we're discussing ionic bonds, where all of the electrons are attracted to one atom and the other one loses it entirely. And that was ionic compounds. But with covalents, they're sharing the electrons, but now there's an unequal sharing, and that produces what's known as a polar covalent. And if they're shared equally, that's called a non-polar covalent. So this is how it differentiates between like a north and a south pole, is because there's a difference in the amount of sharing. One tends to hog the electrons a bit more than the other.
Right, and there are consequences for that, which we'll discuss. So polar covalent compounds basically results from an unequal sharing of electrons. The more electronegative oxygen atom holds the electrons closer to itself. Now within the molecule, what ends up happening is a slightly negative end with respect to the oxygen because of the closer proximity of electrons towards itself, and a slight positive end where the hydrogens are because the electrons are further away from it.
And if you remember your periodic trends from a previous chapter, that is where the unequal sharing results from.
Now, one other thing to note here is that Vesper geometry will also dictate the polarity of certain bonds as well. For instance, there are some certain structures where there is a difference in electronegativity, but because of the Vesper geometry, it ends up not being polar. For instance, carbon tetrachloride would be an example of this. The carbon-chlorine bond is there's a big difference where you'd expect chlorine to be the more polar.
But since you have four of them pulling in four different directions at the same time, it balances out and winds up being nonpolar.
Right, so the symmetry of the molecule and the equal pull in all directions cancels out the potential polarity of that molecule. Polar covalent compounds are also soluble in water, which is itself a polar compound. You might remember from biology, like dissolves like. This is what it's based upon.
And also, non-polar and polars do not mix. This is why oil and water don't mix.
Properties of covalent compounds, because of their polarity and the resulting intermolecular forces, you get different properties. Now, intermolecular forces just basically mean forces that allow different molecules to interact together.
So there's three categories that we're going to go over. First one being hydrogen bonding, and this is the strongest one. Then we have the dipole-dipole, which is less so, and then dispersion, which are the weakest.
Now, I know in this figure on the right they talk about van der Waals, but think of van der Waals and dispersion forces basically being the same thing.
Right, it's just collectively.
So for polar covalent compounds, because they're the compounds that exhibit the strongest intermolecular forces, for instance, hydrogen bonding and dipole-dipole, they have different properties than nonpolar compounds, which essentially only have dispersion forces, whereas polar compounds have two out of the three, whereas nonpolar compounds only have the van der Waals. The dispersion force will be ubiquitous for both.
Right.
Okay, and this results in the ability to dissolve in water, higher melting and boiling points, and the ability to conduct electricity. Excuse me. Hydrogen bonding. Hydrogen bonding basically is a hydrogen from a polar molecule being attracted to a lone pair of electrons in another polar molecule.
And it tends to happen only with four elements: hydrogen with fluorine, oxygen, or nitrogen. And that'll form your hydrogen bonding. And it's the strongest of your intermolecular forces.
Now, it's not like a bond in the sense that it's like a covalent bond or an ionic bond. It's much weaker if you measure them up to either of those two kinds of bonds. However, if you add them up over millions of molecules, they collectively end up being quite strong.
Which is why water can dissolve ionic compounds, but it's not going to entirely rip apart other covalent compounds as well.
So in this figure on the right, you see the attraction Now these little deltas mean like slight positive charge, and the negative means slight negative. So water molecules will attract it to other water molecules or other polar compounds if they're present.
And this causes a meshwork, a network of interconnected water molecules, which gives rise to some of its secondary properties, shown at the bottom down here of adhesion, cohesion, and surface tension.
So these bonds are not permanent. They're constantly being broken and reformed with other water molecules. And again, if you remember as you said before from your biology, your adhesion and cohesion, if you remember those little nature videos of the little water bugs skipping on the surface of the lake or the pond or whatever, right. Those are all examples of hydrogen bonding.
Also why belly flops hurt.
Yes, that too, I guess. Dipole interactions basically is a weaker version of a hydrogen bond. It's less specific. Basically, it's the positive end of one polar molecule attracting the negative end of another one.
So it's similar, but just stronger. And that's about it for that.
Not as stronger.
Oh, no, sorry. Not as strong.
Second strongest.
Yeah.
And again, this only can happen between polar covalent molecules. The last one is dispersion forces. These are basically like dipoles, but they are very weak in the sense that these are dipoles that only result from the random movement of electrons. So they only exist for very small fractions of a second.
Right. So it's temporary and it's random charge separation, and that's what causes them to separate into these poles that will cause attraction.
So it's the weakest of all the intermolecular forces, and all covalent compounds, whether or not you're polar or nonpolar, will exhibit this force.
Right.
I think, is that it? No. Nope. Network solids. Network solids, these are solids that are actually connected together through covalent bonds. It's not like a solid like salt or sugar, for instance, that are just a bunch of molecules stacked together for sugars, or if it's a bunch of oppositely charged ions connected together.
Right, and these result in a very strong three-dimensional structure, more so than the general crystal lattice from ionic solids. And this results in some of the hardest substances on the planet. Actually, the strongest substance, being diamond, is a covalent network solid. And the arrangement of these atoms is what gives these solids their particular physical properties.
Yeah, so these are much different than covalent compounds themselves. So normally, if we compare ionic compounds to covalent compounds, there's no contest. Ionic compounds have much higher melting points and boiling points and stuff like that.
And they're pretty tough.
Whereas network solids, in comparison to the covalent bonds, have much higher properties in terms of temperature for boiling and melting and stuff like that.
Right. And that's it.